This is going to be a lesson on Student Learning Task 4, Quadratics and Complex Zeros. So if you could please turn to page 43, you'll see there are three graphs, and you're asked to graph each function and determine its real zeros. Now I want to remind you that zeros are simply x values that give a y value of 0. Like literally what x values make this function equal to 0. That's what a real zero is. So take a minute and graph these three functions. Okay, so hopefully when you graphed these three functions, you noticed that you had three simple but very different graphs. The first graph moves down 9, and I just plotted points like 1 squared minus 9, 2 squared minus 9, etc. And I found that the real zeros were here at 3 and -3. For graph B, I found it had one real zero at x equals 0, and for graph C, I found it had no real zeros because it never crossed the x-axis. So number 2 says, what do you notice about the zeros of the functions as they relate to the graphs? Well, what I notice is that graph A has 2 zeros and 2 x-intercepts. Graph B has 1 0 and 1 x-intercept. Oops. C has no real zeros. I keep forgetting the word real. Has no real zeros, no x-intercept. Okay, how many zeros did you expect for each of the functions and why? Well, a lot of people say that they expect 2 because most quadratic equations have 2 solutions. Like when we were factoring and solving, or using the quadratic formula to solve, or if we're using completing the square to solve, those equations, most of them had 2 solutions. All right, so what does this have to do with SLT for complex zeros? Well, these graphs, we looked for the real zeros. Take a minute and read the top paragraph on page 44. Okay. So Leonard Euler, similar guy who came up with our favorite number E, came up with the idea that we would have a number that stood for this imaginary number, I, the square root of -1, and he called it I. Okay, this is a very important definition. The idea that we have this new number I, and it's going to be equal to the square root of -1. And he now developed this, what's called the complex number system. The complex number system is composed of all the real numbers and plus all the imaginary numbers. Okay, every complex number takes the form A plus BI, where A is the real number and B is how many imaginary numbers you have. Okay, so it says based on Euler's definition of I, what is the value of I squared? So if we had I equal to the square root of -1, and then we squared both sides, we end up with I squared equals -1. And that's an important fact we want to keep in mind. We want to remember that this is possible because square and square roots are inverse functions. Okay. A radical expression with a negative radicand, remember that's like the argument, the stuff under the radical, can be written BI. for example, the square root of negative 39 can be written as square root of negative 1 times 39, square root of 39, or I root 39, because the square root of negative 1 is just I, and then root 39 is root 39. So it says, how could you rewrite each of the following expressions in the form BI? Now, before I let you do that, I want you to take a look at some other examples I have for you. So let's say we've got the square root of negative 9. Now, we all know that the square root of 9 is 3. So the square root of negative 9 is going to be like the square root of 9 times the square root of negative 1. So the square root of negative 9 is, oops, I don't know what that was all about, 3i. If we had, for example, the square root of negative 100, what's the square root of 100? 10. So the square root of negative 100 would be 10i. Like, you could do this all day. If I had the square root of negative 25, that's now 5i. So the square root of negative 2 is like the square root of negative 1 times the square root of 2. So we've got I root 2. Now I want to point out, if the radicand is made up of a negative perfect square, you see how I put the number first and then the I, number I, number I, because I'm not worried about being confused. 10i. Here with the I don't want it to slide under my radical, so I put it in the front before the square root, because I don't want it to look like the square root of 2i. I want it to look like the square root of 2 times I. So go ahead and try B and C on your own. Okay, hopefully for B, you wrote 2i. And for C, this negative is just going to come down. This negative becomes I, and it's root 10. Number 6 says, how would you rewrite each of the following expressions? So what's kind of nice about I is, with the exception of I squared, I works just like X. So if I've got, for example, if I had 2i plus 3i, that would just be 5i. I treat it just like a variable. So if I have 4 times 3i, that's just going to be 12i. For letter B, if I just square both terms, I'm allowed to distribute the square because this is a product. The square root of 2 squared times I squared. Well, the square root of 2 squared becomes 2. And now we have this I squared. We want to remember, very important, I squared is negative 1. So even though if this was an X, I would just leave it 2x squared. Now I have to think, okay, 2 times negative 1 is negative 2. So for letter C, again, I'm going to multiply normally. 3 times 3 is 9. I times I is I squared. But now I need to remember, can you see that green? I think you can see the green. I'll switch to black. It's going to be like 9 times negative 1. So letter C is going to be negative 9. Right. Number 7 says, which of the expressions in number 6 have a real number value? Why? So when I look at letter A, it's 12i. It only has an imaginary component. When I look at my answer for 6b, my final answer is negative 2. That's a real number value. When I look at my answer for C, I have negative 9. That's a real value. So my answer is going to be B and C because they don't contain I. Number 8 says, the functions below are the same as number 1. Determine the zeros of each function symbolically by writing a related quadratic equation. Which zeros can be rewritten using the number I? How would you rewrite them? So, want to point out, all we're going to do is set these equal to 0 to solve them. All right, so now we're able to see the x-intercept. So now to get the zeros, all we're going to do is solve. So there, you can solve this by factoring or by square roots, like 9 equals x squared. And we would take the square root, and x equals plus or minus 3. Here, just take the square root, big deal, n equals 0, boringest equation ever. So now here's where the fun begins. We go to subtract the 4. and we get negative 4 equals t squared. And until this point, we were like, oh, problem over. No real solutions. Well, now, guys, we have a solution. We can take the square root of negative 4 and get plus or minus 2i. Now, will we see this on the graph? No, we will not, because this is not a real solution. This is an imaginary solution, because it only has an imaginary component. If it had a real component and an imaginary component, and we're going to do one like that, it would be called a complex solution. We'll get there. Okay, so here we go. Page 45 says the numbers in the form a plus bi, where a and b are real numbers and I is the square root of negative 1, are called complex numbers. I like to say if a real number and an imaginary number got married and had a baby, it would be a plus bi. A little bit real and a little bit imaginary, hanging out all by its lonesome. Numbers like 3i and I root 2, I can't read this as root 2 times I, it feels wrong, are called pure imaginary numbers because they are made up of only the imaginary term. Now, up until this point, we have only dealt with real numbers, like our friend R, because that was all real numbers. It didn't have an imaginary component. So how can we determine if a quadratic function has complex zeros from its graph? So what I want you guys to do is pause the video and take a look at the that last graph C. And hopefully you've noticed that things that have complex zeros, there are no x-intercepts. Because I can't spell. The zeros aren't real, only complex. Now maybe it's a pure imaginary number, or maybe it's a complex number. So this says determine the complex zeros of the quadratic functions represented in the graph below. So what I want everyone to do right now is to write down the vertex. Awesome. Hopefully everyone for letter A wrote down that the vertex was 0, negative 2. And hopefully everyone also noticed that this graph is facing down. So I know that this is the function y equals negative x squared minus 2. It's a pretty basic graph to write the equation for. I want everyone to set it equal to 0 and solve. So hopefully you realize that we're going to use square roots to solve. We're going to add 2. We get 2 equals negative x squared. We're going to divide by negative 1. We get negative 2 equals x squared. And then when we take the square root, we get plus or minus I root 2. Now this graph is a little different because it is opening up, so I know A is going to be 1. And I see the vertex is left 2 and up 3. So when I let y equal 0 and I look at this equation, I see this one's also going to be solved with square roots. I'm going to start by subtracting 3. And I know it's solved with square roots because I see it's already written as a binomial squared, for those of you who didn't pick up on that. So I've got negative 3 equals x plus 2 squared. Now when I go to take the square root, now I'm going to have plus or minus I root 3 equals x plus 2. This is like my favorite kind of answer. I love the way this looks, and I don't know why, but I just think it looks very fancy. And I subtract 2, and I get negative 2 plus or minus I root 3. So my graph has complex zeros. The complex zeros have a real component and an imaginary component, but I don't see them on the graph. Even though there's a real component, the imaginary component means it's not going to show up on my real axis. All right, so the best part of this lesson, the whole meat and potatoes, is so now we can start solving equations that may or may not have real solutions. So if you turn to page 47, you will see I have 3 equations laid out for you. I want everyone right now to take a minute and talk in your group about the best method to solve these three equations. Pause the video and talk in your groups about methods. Okay, hopefully you have paused the video and you've had a chance to talk and you've decided that number 1 would be a good one just for square roots. You looked at number 2 and you were like, well, it doesn't factor, and this is an odd number, so this one is getting quadratic formula. And hopefully for number 3, you realize, well, it doesn't factor. And I know that some of you are thinking, but 4 and 2, but 4 and 2. But it's not -8. They both have to be positive, and 4 plus 2 is 6, not 2. Boo-hoo. So this one, we're going to complete the square. All right, so go ahead, pause the video again, and apply these methods to these 3 equations. All right, I'm going to take it all the way down. And again, you should have already done these on your own, to where we used to stop. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. It's 28. Leave a little space. Fill in the little space. I know you love my singing. And then we used to just stop here. So what I've done is I've done all the problems up until the point that we used to stop and say no real solution. And guess what, guys? Now there's a solution! But it's just not real. It is complex. So let's take a look. Number 1, hopefully you were like, okay, no big deal. It's the square root of -16, and you made it plus or minus 4i. This is a nice answer. Oh, that's supposed to be a 5. So now subtract 5 from both sides, and we get this really sweet looking answer of -5 plus or minus 4i. Right, so now over here, we used to just stop at the quadratic formula as soon as we had a negative under the radical, but now we can say x equals -3 plus or minus I root 19 all over 2. Yeah, don't put the I in the back. Nobody puts I in the back. All right, and then this last one, I've got the square root of -7, so it's going to be x plus 1 equals plus or minus I root 7, and then we're going to subtract the 1. We have an equally sweet looking answer like number 1. And so now we are able to solve quadratics that don't just have real solutions, but also have complex solutions. Your homework tonight is actually going to have you do this. Your homework tonight is going to be to solve these super awesome equations. And you will notice that you are going, no, actually I'm a big fat liar. It's 1 to 6. I read the wrong assignment. It's explore more on the back, 1 to 6. Yeah. That's kind of boring. If you want to work on some of these guys just for funs, maybe like 7. 7's a good challenge.